Hello everyone, and today I'm going to show you how to use this geometry node rating system. This is the same behavior as the old armature modifier. So it gives you everything of this armature modifier here. Let's select the object, we have the vertex group, and for the preserved volume, it internally should use an algorithm called dual quaternion skinning. By default, this is AirBS, which is linear blend skinning. And the preserved volume using dual quaternion. Multi-modifier, I'm not sure about that. I don't use that actually, so I'm not sure what's that. But let's take a look at this one here. So this is the reference papers that I used. So there are mainly 4 algorithms. The first one is AirBS here. The second one is the DQS. And there is also a composition for this DQS to make it look better, and we also have a paper implement. It's Disney paper, which is the optimize the center of rotation. So basically this paper, what does this paper doing? It calculates a least square transform, which is a least square radius transform, so that this one without volume shrinking, and also doesn't have this Bauge effect of the DQS. And we also have a dot mesh. Dot mesh is just the modifier of the that's the smooth corrective. So this one is actually the dot mesh algorithm. So what does this do? It smooths the geometry, and then after we deform, then we add that dot back, which is just the original one. So basically, imagine that this is our geometry, and then you smooth it. Then you deform the smoothed version, which is something like this. And then previously, you smooth it from this geometry to this geometry, and you store that difference inside each vertex is TBN matrix, which is tangent, bitangent, and normal. So you store it into his local tangent space. After you deform it, then you will add that difference based on this current tangent space. So you add that back, you will probably get something like this. So this is how this algorithm works, the dot mesh. And previously we also used this item, but this item from the locus toning seems broken in 5.2 and 5.3, because previously this node, how we build a list is using this node, but this is changing in 5.1. So this item is made in 5.1, and 5.1 this node is simply called list instead of field to list. So I guess this name difference caused this item to broken. No, I don't know why. Yeah, but I just make another version right now, because we have the attribute name. So we just select a skin, and the skin will contain all the vertex groups of the bone. So we can just extract the bones from here. But this is just a simple way, because this item actually gives you a lot of more information, like the connection relationship between each bones and other stuffs. So it gives you a lot of information, which is quite handy. So that's the brief view of it. So let's look at the actual node. First, here we have two nodes to build the skeleton inside the geometry node. And then we have the basic weight capture, which just use a capsule or a line segment to do a simple bone capture. Then we have a transform from the local to world or the world to local. So here we also have a forward kinematic, where you just define the transform matrix. And here is also a basic skeleton simulation here. So let's take a look at the difference between each one here. So as the bone deform here, we can see that RBS, which is a linear blend skinning, is shrinking the volume here. So as we can see, there is shrinking the volume, while DQS is using rotation to avoid the volume shrinking. But because that is purely rotation, so here we can see it created this Bogey artifact. And there is a quick fix of this DQS algorithm, which looks like this. It's kind of working, but it's still not very smooth. And the last one is the distance optimized center of rotation, which calculates a least square rigid deformation, and then it will look like this. So which keeps the volume and doesn't have this Bogey artifact. So typically this one will give you the best result. And also we have the dot mesh here. And as you can see, this one is pretty ready to transform here, and you will see this dot mesh is very smooth. As you can see, this one is definitely much smoother than this one, and these two pretty much the same. Yeah, it's pretty much like the linear blend skinning. And yeah, like this one, you have this candy wrapper issues, where you lost all the volumes when you rotate 360 degrees. The DQS works perfect for this case, and same as this one. And the dot mesh only fixing a little bit, but still not working in this extreme case. So that's this demo here. And the ragdoll. The skeleton simulation is just a very simple ragdoll here, we can see. It's just a very basic ragdoll simulation, where you can rotating it like that. So this is procedural rigging in geometry node here. You can see the original mesh, and this is the deformed version. So this string is related to the skeleton transform. And then here we will do a bone capture, because typically what you will do is loop through our bones and get the bones transform, then accumulate all the bone transform for each vertex. But for example, for your human skeleton, you usually have 100 bones. And then you can just loop through our bones like 100 iterations. That will be too laggy for real-time deformation purpose. So here we can do a compressed bone weight. So it will loop through the 100 bones, and then for each vertex, it will get the bone that will affect this deformation. For example, like this vertex here, in theory, it should only be affected by this bone and this bone. So it will only store that two informations, that two bones, without storing our bones. So here we compress the bone weight, and it will reduce the iteration count from 100 to something like 2, which can be used in real time right now. but because this is jump node calculation, so it's still a little bit slower than the native implementation of the modifier. I guess it's roughly 3 times or 2 times or 3 times slower than this old armature modifier, but it's still good for real-time purpose. This one, and then here we have computed the center of rotation or the dot mash. So this is a compressed weight, and after that we have some pre-computations. Yeah, because this needs center of rotation and the dot mash. It can be pre-compute some informations and used later. So we can pre-compute it and then bake it. So later on, this algorithm will run much faster. And then here is the actual bone deform, where you give it a provided skin and then the deformed skeleton. And then you choose the algorithm here. And here is some utility mask here. Because for this needs optimized center of rotation, I make a quick approximation for it. So it happens. It has a little bit of error, obviously. So let's see what's going on. Let's see this one here. Okay, something is not working. Okay, let's bake it. Okay, here we can see this is a animation from the maximal, and we procedurally deformly inside the geometry nodes. So this is the model here. This is the deformed skeleton, and then this is bone deformed results. And let's see. Yeah, this is a little bit weird. So let's see. And keep 5 bones here. Let's recapture it. Yeah, as we can see, for this version, it seems broken for this unique part. Or it looks great, but for this hand, it seems a little bit wrong. Okay, I think that's a capture weight. Yeah, let's rebake it. Okay, it's still broken. That's weird. Maybe let's capture more bones. I'm not sure why. This is too weird. I guess maybe something wrong with the skeleton. Because in the 5.1 version, where I use the locus item, that doesn't seem to happen. This is so weird. Previously, this doesn't happen. It only have a few vertices that have a little bit offside, like a small specks. But right now, it looks so weird. So yeah, this one's weird, but for RBS, let's see. That one's still wrong. Okay, so there is no issue, I guess. It's just something wrong with this armature extractation. So if this item can be fixed, we use this item, then that would be fun. Maybe it's something wrong with the skeleton. So for this one, let's see. It also happens. So let's just ignore this one. Something wrong with that. So this is a little mask for the arrows. which I previously used for detecting the arrows backkeys for this one. And this is a joint mask. And this is a post process for the DQS, as we say in here, which is the quick fix of this body artifact. And then there have two visualize utilities, where you can visualize the bone weight like this. You visualize the weight for a specific bone, and we can visualize the skeleton here, which just visualize it like this one here, showing it like a bone shape. So that's all the node group. And let's take a look at the setup here. So that's from the RBS here. So the basic setup is just we have the basic model, the skin geometry. Then if you doing a procedural rigging instead of geometry node, you will use the skeleton from the edge. So you provide a mesh edge, then it will build the skeleton for it. And you define a root joint after this, and then you will doing this forward kinematic. So here we're doing some transform here of the bone here, and then we can visualize the rigging here, which is just the bone here. You can see this is a forward kinematic animation here. The forward kinematic is just this is a root bone, this is a child. So when you deform the child bone, then you will, for example, you deform this one, then you will also deform this one. Let's see here. Yeah. For example, if you rotate the parent bone here, then it will also rotate this child bone here. So inverse kinematic is where you modify this root, which is the child bone here, and then it will automatically calculate the transform for this parent bone here. So that's the inverse kinematic transform. And for the forward kinematic, where you modify the parent transform, then for the child, it will also do the parent transform. So that's just a simple rigging. And then here we will do a bone capture here, and you can visualize the capture result. So you can see it's just two bones, and this is the weight of the bone, which using the line shape or the capsule shape. The line shape is calculates the distance towards to the line, and the capsule shape where you build a capsule here, and then you will compute the capsule as df. And that's just some settings, and you can blur the weight a little bit to make it smoother. And after that, we're just doing a bone deform, where take the skin and the deformed skeleton here, and then choosing the algorithm here, and then it will just look like this. For the DQS, pretty much the same settings, but here we use the DQS algorithm here. And for this body-free DQS, which is just a post-processing here, and you choose the DQS, and then that's the result. You're doing a little bit fix here. So that's the previous here, and after it, you can control the strings here. Also, we can smooth it a little bit. Yeah. But that's it. And for for this version is a little bit different. Yeah, for this base version we need to pre-compute some stuff and also bake it here. So let's take a look. So still this bone capture here, and then afterward we can just compress the bone here. And you will notice there's a skeleton socket. For this socket it is used in here, which you here. For example, your skin geometry is gathered from this object here, and then you will do a compressed bone weight, because this skin geometry is directly gathered from this model here, so it doesn't know about the skeleton information here. So this socket is just to provide some skeleton information for it to compute. Otherwise, this model doesn't have any information about the skeleton, so we will use it. So this socket doesn't do anything, it just provides some information here. So in this case, because your skin is captured using the bone capture, so it knows about the skeleton. It have all that information, so we don't need to use this socket anymore. And then here we can manually define how many bones we want to keep, and this is a threshold, which is a threshold here. Or we can automatically detect it. So if this bone weight is higher than this number here, then it will automatically consider this is as a valid bone and record that bone. So just take it menu, and then we need to compute the center of rotation. So this is a pre-computation here, and you will see here, this is the original implementation. This is the full implementation of the paper here. Because this is loop through our bones here and then loop through our vertex, so this one is super lucky. It can be used. Then I optimize the algorithm a little bit. Here we assume that one vertex will only be affected by two bones, which is just like this joint here. You're only affected by this bone and this bone. So with this assumption, then this can be computed much faster here, but it still takes some time. So after this process, after we compute this one, all this is pre-computation here, so we can just bake it, and then it no longer need that, so we can just bone deform it very fast here. Yeah, this algorithm itself is pretty much like an RBS process, but it just requires the optimized center of rotation, where you compute a optimized center for each of the vertex and then use that center to do the deformation here. So after baking it, then this will still be real time here, as we can see here. That's this algorithm here. And for the dot mesh here, again we need this one is not necessary, I think. Yeah, for this one it doesn't require the compressed, but it's good to keep the compressed, because this step can reduce the bone amount here, and that's because we only have two bones here, so this compress doesn't do anything. But for example, if you want to use a human skeletons, then you will have 100 bones and or more, so it's necessary to compress the bone weight here, so that it can be running much faster here. And then for this one, we have a compute data here. So, okay, this is the old version. Let's use a data mesh here. by doing compute here. And then for this data march here. Here you can see. So if you use the bone deform here, this version requires a pre-computation here. So the data march has three modes. The first one is compute. The second one is the apply. So instead of the bone deform internally, it uses the apply mode. So that require us to pre-compute the data march information. And it also have a third mode, which is compute and apply here. So we have a compute and apply here. For example, let's see, we can show it in the RBIs here. So for example, here is our deformed geometry. Let's see, that's our deformed geometry here. Let's use this one, and also a rest geometry here. So you can see this one is shrinking a lot, and then you can compute and apply it. Okay, something. Okay, I should use this one here. Yeah, that's the previous one here, and this is the after here. You can make it more smooth here, the previous and the after here. So you require a deformed skin and a rest skin, and then you can compute and apply it all at the same time. The smooth iteration and the weight and the strength of it. Okay, so that's a quick view of all the setup here, and you will visualize the bone weight here. Okay, that's we compress it. Yeah, you don't tackle the clean weight. So what does the clean weight doing here? It has the joint 0, joint 1, joint 2, which is the bone weight by the bone capture here. Then you compress the weight, so it will compute the compressed bone weight here, as we can see. If you clean the weight, then it will just clean the previous attribute here. So you can clean the R0. So by default, let's leave it not clean, so that we can visualize the bone weight here. So where you select a joint index, and then you can visualize it here. But for example, if you don't know about the joint index, you don't know what the index is, this bone here, you don't know its bone index, you can visualize it in here, where you can show the bone name here. So with this visualize rig, it has the X direction and the Y direction. Also, it's showing the bone name here. You can see the name is the joint 1, joint underscore 1, and his index is 1. And for this one, his index is 0 here. So you can use this node to visualize the name and the index for this bone. So that's this setup, and let's see this demo. This is a ragdoll simulation here. So let's say this setup here. This setup, we get the body mesh here. Then there's still a edge here. So it will specify the bones here, which is the root here, and then you're doing a skeleton from the edge here. Then bone capture it procedurally using the capsule shape here. Then we compress the bone weight here. and then you can visualize the weight for each of the bone here. So that's the weight for each of the bone. Then you need to bake it. Then after the bake here, then we can just do in the bone deform here. Okay, so here is also the skeleton simulation here, which is a quick ragdoll setup here. So this one you define a gravity here, and the dot time, subsnap here, and the skeleton edge, and the velocity damping, and you can do some lock here. So let's see which one is been locked here. Yeah, which is the shoulder here and this part here. So where it locked, then it will lock the angle here between this range, which is 0 and 30 degrees here. It will clamp his deformation, clamp his rotation angles inside this range. If it doesn't been locked here, then it can be freely deformed. Then we also have a pin here, which just pin the root bone here, and to be this controller transform here. So that's the setup here. Then you are doing a deformation here to deform this one here. Okay, so that's the setup. And there is a quick pudding setup where I deform this pudding here. So we can transform it like that. Yeah, this is not perfectly smooth. Just a demonstration of it. So same setup here. This is building the same setup here. Make the procedural model here. I'm doing the bone capture here. And also this one here. So let's get rid of this one here. And we have a skeleton transform here. Skeleton simulation. So you will see this is wiggling here. And then you're doing the bone deform here. So that's a setup. Same thing for this one here. This is the geometry, doing the bone capture, the skeleton simulation here. And then compress it, then bake it. Then we can deform it like this. For this maximal animation here is getting a little bit wrong. Yeah, I don't know why. This one is a bit wrong here. Okay, so that's pretty much all. So this way let you doing procedural rigging inside of geometry nodes. So the algorithm is the same as the modifier here. So we just waiting for the future that the devs can add a proper skeleton node inside of geometry node to extract all the bones here. Currently, this one is not perfect. This is not perfect. This is just a simple way to get the transform here.